Hello everyone, this is my lab 4 about circuits for Physics 20 to 12. The goal of this lab is to study electric interactions of capacitors in circuits. First, we experimented with resistors in series and in parallel and how different arrangements affected voltage and current in the circuit. Then we studied how capacitors change and discharge through exploring interactions with two different light bulbs. And finally, we measured time-dependent voltage in the RC circuit. Since I was experimenting with this circuit virtually, it has eliminated most sources of potential error, which could have existed if I used real circuit equipment from the lab. On the right side of the slide, you can see main physical principles that I have used for this lab. The two main rules are the node rule and the loop rule. We can also call them current and energy conservation respectively. Also, I used this formula to calculate capacitance in a capacitor and Ohm's law to determine current. The lab consisted of the two main parts. First, experimenting with charge conservation and energy conservation in circuits, and then experimenting with RC circuits. Here is a summary of the main results. For the first part, I worked with 3 different models, and then with 2 for the second part. I will talk about these results and conclusions in more details in the following slides. Now let's talk more about charge and energy conservation. On this slide, you can see my measurements and observations for the first model that includes 2 batteries, 1.5 volts each, 2 ampermeters, and 2 resistors, 47 and 100 ohms respectively, connected in series. Using Ohm's law, I have calculated the predicted current by dividing voltage over total resistance, which is equal to the sum of resistance values on each of the 2 resistors, since they're in series. So 100 plus 47, so the total resistance is 147 ohms. On the right side of the slide, you can see the screenshot of the circuit built in CCK. As you can see on the screenshot, the predictions were correct and the ammeter measured 0.02 amps. Note, when we replaced ammeter with a voltmeter, it measured 3 volts. I have also observed that when we reversed connections to one of the ammeters, we obtained the same measurements. On this slide, you can see measurements and observations on the same circuit but at different segments, as indicated on the first screenshot on the right side. At the bottom left corner, there is a table recording potential differences at each of the segments, and at the bottom right, I have included a complete graph illustrating potential. As predicted, the fact that potential difference is 0 on some of the segments illustrates the loop rule and the correctness of the data. Now for the final model of this part, I have calculated resistance of the resistors, wire, and ammeter when one of the ammeters was placed in parallel with one of the resistors, as shown on the screenshot on the right side. Using node rule for predictions, both of the ammeters indicated 0.06 amperes. Finally, at the bottom, you can also find calculations for resistance using Ohm's law, dividing voltage by current for each of the elements in the circuit. Now moving on to the second part of the lab, RC circuits. In this part, we focus on RC circuits that included 20 or 10 ohm light bulbs, 2000 microfarad capacitor, and a 9 volt battery. When battery, light bulb, and the capacitor are connected, the light bulb is very bright at first and then it dims. The process happens because the capacitor gains charge and resistance. Similar process happens when we remove the battery and the capacitor begins to discharge. The light bulb is again very bright at first and then gets dimmer over time. I have recorded charging and discharging times for each of the 2 cases on the left side of the slide. And on the right side is a digital circuit model from CCK. By measuring the amount of time it takes for a light bulb to get brighter or dimmer given different resistances, we have observed that the time it takes to discharge or charge the capacitor is directly proportional to resistance. Specifically, the higher the resistance, the more time it takes to charge or discharge a capacitor. Now, moving on to the last model of this lab. Here we focus on the time-dependent voltage across a discharging capacitor. An important fact to remember here is that potential difference decreases as capacitor discharges. So the main goal here is to calculate RC times by measuring and then plotting potential difference values through time. On the right, I have included a screenshot of the digital circuit model that I used for my measurements, which is the same as the model on the previous slide. Here on the left side, I have included collected data that I also used to plot the chart on the right. It turned out that using the equation obtained from the plot, RC time is approximately 6 seconds, which matches the expected value. Finally, 2 reflection questions. Answering the first one, I think the current readings on the ammeter would be smaller since there would be additional resistance due to real ammeter. And answering the second question, I think that it would take longer to charge the real capacitor with a real battery, since then there will be an internal resistance present inside the battery. Thank you everyone so much. This is it.